All right, so for this last section, we're going to be looking at a specific physical change, and that involves heating up a substance. And so what you see, this graph that you see here, this is called a heating curve. So if you notice, you start at negative 40, this is for water specifically, and you start with a solid. And so if I put heat into this, if I'm heating up this substance, the first thing that would happen would be that solid would increase in temperature until it hit 0 degrees. Once it hit 0 degrees though, it would actually stop increasing in temperature, and all of that energy would be spent in converting it from a solid into a liquid. So that is the process of melting. So I'm going from a solid to a liquid. Notice the temperature doesn't change. Then if I kept putting energy into that, then the liquid would increase in temperature. So if I keep putting in heat, the temperature increases. It stops right here at 100 degrees Celsius, which is the boiling point. So it's still a liquid right here. Then if I kept putting energy in, this would convert from a liquid to a gas. It would vaporize. And if there was some way that you were able to collect that vapor and continue to heat it, then it would become a gas. Sorry, then it would be, it is a gas, then the temperature of the gas would increase. So you'll see that right there. All right, so all of these processes, whether you're increasing temperature or you are melting or vaporizing or boiling, that requires energy. So energy, as I'm moving from left to right on this graph, is increasing because I'm putting energy in. So we call this an endothermic process. Endothermic meaning you're putting in energy. If instead I went backwards on this heating curve, meaning I'm removing energy. So if I'm going from a gas to a liquid, for example, or a liquid to a solid, I'm moving backwards, heat is actually released. So it's an exothermic process. So when an endothermic process happens, energy is put in, and so what you would feel is actually cold. And then if you have an exothermic process, heat is being released, so what you would actually feel is hot. So weirdly enough, when you walk near a refrigerator or a freezer, the air that's coming off of that freezer is actually warm because the energy that is being released so that the liquid can become a solid, it is released from the freezer. And so that's why we actually feel hot air when you're walking by a freezer. So how in the world do we calculate the energies instead of just talking about, oh, we're increasing temperature here, we're melting here, we're increasing temperature here, we're vaporizing or boiling here? How can we actually calculate the energy that's involved? Because that's what we're going to be doing. Well, if we are going from a solid to a liquid, I'm melting, then the heat is going to be positive because it's endothermic, energy is being put in. If I'm going from a liquid to a solid, I'm going backwards, it's exothermic, so your heat is going to be a negative value. So how do I actually calculate this numerically though? Well, I'm going to use what's called my heat of fusion. And my heat of fusion is the quantity of heat needed to melt 1 gram of a substance. Okay, and if you look at the practice problem that I gave you, joules are your unit of energy, so that is the amount of heat, that is your energy for every 1 gram. So that is your heat of fusion. Now note, your heat of fusion, if you're going from a solid to a liquid, is going to be positive, and it would be negative if you were freezing. So if instead of melting this ice, what if I were freezing the water to make ice? Then your heat of fusion would simply be negative 334 joules per gram. So let's do this practice problem. I start off with 15.5 grams of ice. So I'm going to start with 15.5 grams of ice, and I want to figure out how much energy or how much heat is absorbed. So I'm going to get out of grams and I'm going to get into joules. And I'm going to use my heat of fusion here. So 334 joules for every 1 gram. So in my handy dandy calculator, I am now going to take 15.5 and I'm going to multiply that by 334. And I get, for my unrounded value, 5,177 joules. 15.5 has 3 sig figs, 334 has 3 sig figs as well. So I'm going to round this to 5,180 joules. And that's my answer. Okay, so that was melting. That's great. What if instead of freezing or melting, I want to vaporize? So this is your heat of vaporization. So just like your heat of fusion, if I'm going from a liquid to a gas, whatever your vaporization is, that heat, it's going to be a positive value. If you're going, because it's an endothermic process. If you're going from a gas to a liquid, it's going to be a negative value because it's an exothermic process. So what is your heat of vaporization? It is the amount of heat needed to vaporize. Remember, vaporizes go from a liquid to a gas. Vaporize 1 gram of a substance. All right, so let's do a little practice with this. All right, so for this example, how much heat in joules is required to vaporize 33.8 grams of water if the heat of vaporization is 2,260 joules per gram? So I start with 33.8 grams. I'm going to get out of grams, and I'm going to get into joules, my unit of energy. Now notice my heat of vaporization is a lot larger than the 334 that it was for the heat of fusion. And this is all just for water. Each substance has a unique heat of fusion and heat of vaporization. And the reason why it's so much higher is, if you think about it, to melt a solid, you're breaking some attractions between those particles. But to turn it into a gas, there are no longer going to be any sort of attractions between the particles. So it requires a lot more energy to vaporize, or a lot more heat to vaporize than to melt. So I'm going to multiply this out, and I get for my answer 76,388. I want 3 sig figs, so I'm going to keep this as 76,400 joules. I just want to really quickly show you, I just said that the heat of vaporization is always much larger than the heat of fusion. If you look back at your heating curve, you can see how much longer of a line this is, right? So this is showing that more energy is required to convert something from a liquid to a gas than from a solid to a liquid. And that's just because the attractions for going from a liquid to a gas, you're trying to break them apart completely. While for a solid to a liquid, there are going to be some attractions still between the liquid molecules. So you're not breaking all of those attractions. All right, so that's wonderful. Sorry for that. But we just talked about heat of fusion. We talked about heat of vaporization. What if we're not changing state of matter, but instead we're changing temperature? If we're changing temperature, we got one more concept to talk about, and that is your specific heat. Okay, so your specific heat is the amount of heat required to increase the temperature of a substance by 1 degree Celsius. Okay, and specifically it's 1 gram of a substance. So the amount of heat needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. All right. So the formula for this is not just like a conversion like we did before, because it's not, the units are not just joules per gram. Now we're specifically increasing temperature. So there's another factor we have to take into account. So our heat, this is represented with a Q, so the heat equals the mass of your substance, just like I had before, times your specific heat. But now we have to take into account our change in temperature as well. Okay, so just a quick refresher. Your Q is your heat, M is your mass, and it is in grams. Okay, your change in temperature, the way you find change in temperature, you take the final temperature and you subtract the initial temperature from it. Okay, and then your specific heat, the units for that, just like before, it's joules over grams, which is what we saw with heat of fusion and heat of vaporization, degrees Celsius. So we're also taking into account the change in temperature. Alrighty, so let's look at a practice. Calculate how much heat in joules must be added to 50 grams of water to raise its temperature from 17 to 37 if the specific heat of water is 4.18 joules per gram degree Celsius. So really quickly to find my change in temperature, my delta T, I'm going to take my temperature, my final temperature, and I'm going to subtract my initial temperature from it. So I do 37 minus 17. Be careful when you write this answer because you get 20. But keep in mind, because we want no decimal places, we got to put a dot there so that I know that it should be 2 sig figs and not just dropping a sig fig randomly. Okay, so I'm solving for my heat. My Q equals my mass, which is 50 grams, times my specific heat, which is 4.18, times my change in temperature, which is 20 point. Okay, so I'm going to take my calculator and I'm going to just do that math out. So only new thing here is that you're also changing temperature. And so I'll have to take that into account when you're doing your calculation. So I get 4,180. Okay, 20 degrees Celsius has 2 sig figs, so I'm going to round this to 2 sig figs. And my units are joules. So that is the amount of heat needed to raise the temperature by 20 degrees Celsius. Okay, so last thing we're going to do, let's put it all together. Okay, so I'm going to actually move this up here so we can see this better. All right, draw a heating curve. I'm going to draw a heating curve for ice. So again, we're dealing with water. So I know that my melting point is 0 and my boiling point is 100. Any other substance, guys, I don't expect you to memorize freezing and melting points. I will give them to you. They're unique to that substance. It says draw a heating curve for ice at negative 35 degrees Celsius. So it's going to start here below 0, being changed into water at 30 degrees Celsius. So it is going to be somewhere, I'm going to say like right around here that we're going to end, right? We're not to that boiling point of 100. So my first step, I need to go from negative 35 and I need to get to 0. That's my first step. So that's step number 1. Then my next step, I need to go from a solid at 0 degrees Celsius to a liquid. I need to melt. So I'm going to draw it like that. So that's step 2. And then for step 3, I need to go from a liquid at 0 degrees Celsius, and I need to increase the temperature until it hits 30. So really quickly, I know the question didn't ask you to do this, but I'd love to see you guys do this, especially for the practice. Your first step is to go from a solid at negative 35 to a solid at 0 degrees Celsius. Okay? Then your next step, step 2, is to go from a solid to a liquid. Remember, temperature here doesn't matter because you're not changing temperature for step 2. And then for number 3, you're going to go from a liquid at 0 degrees Celsius to a liquid at 30 degrees Celsius. Okay, so let's bring all of this together now. All right, if I were to ask you, which I will in class, not yet, but if I were to ask you to figure out the heat required to go from ice at negative 35 to water at 30, first step, number 1, you're going from a solid at negative 35 to a solid at 0 degrees Celsius. You're changing temperature. You are going to be using the specific heat, that's represented with that C, of solid ice. So I would have to give that to you and you would do that calculation. For step 2, you're going from a solid to a liquid, so you would need to use your heat of fusion and do that calculation separately. And then for the last step, again, you're changing temperature, so you're going to use the specific heat of liquid water. And when you're done, you would take all 3 of the heats that you calculate and you would add them together, and that would be the heat required to make those 3 total steps.